A micrometer, sometimes known as a micrometer screw gauge, is a device incorporating a calibrated screw widely used for precise measurement of components in mechanical engineering and machining as well as most mechanical trades, along with other metrological instruments such as dial, vernier, and digital calipers. Micrometers are usually, but not always, in the form of calipers, which is why micrometer caliper is another common name. The spindle is a very accurately machined screw and the object to be measured is placed between the spindle and the anvil. The spindle is moved by turning the ratchet knob or thimble until the object to be measured is lightly touched by both the spindle and the anvil. Micrometers are also used in telescopes or microscopes to measure the apparent diameter of celestial bodies or microscopic objects. The micrometer used with a telescope was invented about 1638 by William Gascoigne, an English astronomer. Colloquially, the word micrometer is often shortened to mic or mic. History of the device and its name. The word micrometer is a neoclassical coinage from Greek mikros, meaning small, and metron, meaning measure. The Merriam-Webster Collegiate Dictionary says that English got it from French and that its first known appearance in English writing was in 1670. Neither the meter nor the micrometer as we know them today existed at that time. However, the people of that time did have much need for, and interest in, the ability to measure small things and small differences. The word was no doubt coined in reference to this endeavor, even if it did not refer specifically to its present-day senses. The first ever micrometric screw was invented by William Gascoigne in the 17th century, as an enhancement of the vernier. It was used in a telescope to measure angular distances between stars and the relative sizes of celestial objects. Henry Maudslay built a bench micrometer in the early 19th century that was jocularly nicknamed the Lord Chancellor among his staff because it was the final judge on measurement accuracy and precision in the firm's work. The first documented development of handheld micrometer screw calipers was by Jean-Laurent Palmer of Paris in 1848. The device is therefore often called Palmer in French, and Tornillo de Palmer in Spanish. The micrometer caliper was introduced to the mass market in Anglophone countries by Brown and Sharp in 1867, allowing the penetration of the instrument's use into the average machine shop. Brown and Sharp were inspired by several earlier devices, one of them being Palmer's design. In 1888 Edward W. Morley added to the precision of micrometric measurements and proved their accuracy in a complex series of experiments. The culture of toolroom accuracy and precision, which started with interchangeability pioneers including Griboval, Towsett, North, Hall, Whitney, and Colt, and continued through leaders such as Maudslay, Palmer, Whitworth, Brown, Sharp, Pratt, Whitney, Leland, and others, grew during the machine age to become an important part of combining applied science with technology. Beginning in the early 20th century, one could no longer truly master tool and die making, machine tool building, or engineering without some knowledge of the science of metrology, as well as the sciences of chemistry and physics. Types, basic types. The topmost image shows the three most common types of micrometer. The names are based on their application. Outside micrometer, typically used to measure wires, spheres, shafts and blocks. Inside micrometer, used to measure the diameter of holes. Depth micrometer, measures depths of slots and steps. Specialized types, each type of micrometer caliper can be fitted with specialized anvils and spindle tips for particular measuring tasks. For example, the anvil may be shaped in the form of a segment of screw thread, in the form of a V-block, or in the form of a large disc. Universal micrometer sets come with interchangeable anvils, such as flat, spherical, spline, disc, blade, point, and knife edge. The term universal micrometer may also refer to a type of micrometer whose frame has modular components, allowing one micrometer to function as outside mic, depth mic, step mic, etc. Blade micrometers have a matching set of narrow tips. They allow, for example, the measuring of a narrow O-ring groove. Pitch diameter micrometers have a matching set of thread-shaped tips for measuring the pitch diameter of screw threads. Limit mix have two anvils and two spindles, and are used like a snap gauge. The part being checked must pass through the first gap and must stop at the second gap in order to be within specification. The two gaps accurately reflect the top and bottom of the tolerance range. Bore micrometer, typically a 3-anvil head on a micrometer base used to accurately measure inside diameters. Tube micrometers have a cylindrical anvil positioned perpendicularly to a spindle and is used to measure the thickness of tubes. Micrometer stops are micrometer heads that are mounted on the table of a manual milling machine, bedways of a lathe, or other machine tool, in place of simple stops. They help the operator to position the table or carriage precisely. Stops can also be used to actuate kick-out mechanisms or limit switches to halt an automatic feed system. Ball micrometers have ball-shaped anvils. They may have one flat and one ball anvil, in which case they are used for measuring tube wall thickness, distance of a hole to an edge, and other distances where one anvil must be placed against a rounded surface. They differ in application from tube micrometers in that they may be used to measure against rounded surfaces which are not tubes, but the ball anvil may also not be able to fit into smaller tubes as easily as a tube micrometer. Ball micrometers with a pair of balls can be used when single tangential point contact is desired on both sides. The most common example is in measuring the pitch diameter of screw threads. Bench micrometers are tools for inspection use whose accuracy and precision are around half a micrometer and whose repeatability is around a quarter micrometer. An example is the Pratt & Whitney Supermicrometer brand. Digit mix are the type with mechanical digits that roll over. Digital mix are the type that uses an encoder to detect the distance and displays the result on a digital screen. V-mix are outside mix with a small V block for an anvil. They are useful for measuring the diameter of a circle from 3 points evenly spaced around it. An example of when this is necessary is measuring the diameter of 3 flute end mills and twist drills. Operating principles. Micrometers use the principle of a screw to amplify small distances into large rotations of the screw that are big enough to read from a scale. The accuracy of a micrometer derives from the accuracy of the thread forms that are at its heart. In some cases it is a differential screw. The basic operating principles of a micrometer are as follows. The amount of rotation of an accurately made screw can be directly and precisely correlated to a certain amount of axial movement, through the constant known as the screw's lead. A screw's lead is the distance it moves forward axially with one complete turn. With an appropriate lead and major diameter of the screw, a given amount of axial movement will be amplified in the resulting circumferential movement. For example, if the lead of a screw is 1 ohm, but the major diameter is 10 ohm, then the circumference of the screw is 10 I, or about 31.4 ohm. Therefore, an axial movement of 1 ohm is amplified to a circumferential movement of 31.4 ohm. This amplification allows a small difference in the sizes of two similar measured objects to correlate to a larger difference in the position of a micrometer's thimble. In some micrometers, even greater accuracy is obtained by using a differential screw adjuster to move the thimble in much smaller increments than a single thread would allow. In classic-style analog micrometers, the position of the thimble is read directly from scale markings on the thimble and shaft. A vernier scale is often included, which allows the position to be read to a fraction of the smallest scale mark. In digital micrometers, an electronic readout displays the length digitally on an LCD display on the instrument. There also exist mechanical digit versions, like the style of car odometers where the numbers roll over. Parts. A micrometer is composed of frame, the C-shaped body that holds the anvil and barrel in constant relation to each other. It is thick because it needs to minimize flexion, expansion, and contraction, which would distort the measurement. The frame is heavy and consequently has a high thermal mass, to prevent substantial heating up by the holding hand fingers. It is often covered by insulating plastic plates which further reduce heat transference. Explanation: if you hold the frame long enough so that it heats up by 10 degrees Celsius, then the increase in length of any 10 cm linear piece of steel is of magnitude 1/100th ohm. For micrometers this is their typical accuracy range. Micrometers typically have a specified temperature at which the measurement is correct. Toolrooms are generally kept at 20 degrees Celsius, 68 degrees Fahrenheit. Anvil, the shiny part that the spindle moves toward, and that the sample rests against. Sleeve/barrel/stock, the stationary round part with the linear scale on it. Sometimes vernier markings. Lock nut/lock ring/thimble lock, the knurled part that one can tighten to hold the spindle stationary, such as when momentarily holding a measurement. Screw, not seen, the heart of the micrometer, as explained under operating principles. It is inside the barrel. Spindle, the shiny cylindrical part that the thimble causes to move toward the anvil. Thimble, the part that one's thumb turns. Graduated markings. Ratchet stop, not shown in illustration, device on end of handle that limits applied pressure by slipping at a calibrated torque. Reading, Imperial system. The spindle of an Imperial micrometer has 40 threads per inch, so that one turn moves the spindle axially 0.025 inch, equal to the distance between two graduations on the frame. The 25 graduations on the thimble allow the 0.025 inch to be further divided, so that turning the thimble through one division moves the spindle axially 0.001 inch. Thus, the reading is given by the number of hole divisions that are visible on the scale of the frame, multiplied by 25, plus the number of the division on the thimble which coincides with the axial zero line on the frame. The result will be the diameter expressed in thousandths of an inch. As the numbers 1, 2, 3, etc., appear below every fourth subdivision on the frame, indicating hundreds of thousandths, the reading can easily be taken. Suppose the thimble were screwed out so that graduation 2, and 3 additional subdivisions, were visible, and that graduation 1 on the thimble coincided with the axial line on the frame. The reading would then be 0.2000 plus 0.075 plus 0.001, or 0.276 inch. Metric system. The spindle of an ordinary metric micrometer has 2 threads per millimeter, and thus one complete revolution moves the spindle through a distance of 0.5 millimeter. The longitudinal line on the frame is graduated with 1 mm divisions and 0.5 mm subdivisions. The thimble has 50 graduations, each being 0.01 mm. Thus, the reading is given by the number of millimeter divisions visible on the scale of the sleeve plus the particular division on the thimble which coincides with the axial line on the sleeve. Suppose that the thimble were screwed out so that graduation 5, and 1 additional 0.5 subdivision were visible, and that graduation 28 on the thimble coincided with the axial line on the sleeve. The reading then would be 5.00 plus 0.5 plus 0.28 equals 5.78 ohm. Vernier. Some micrometers are provided with a vernier scale on the sleeve in addition to the regular graduations. These permit measurements within 0.001 mm to be made on metric micrometers, or 0.0001 inches on inch system micrometers. The additional digit of these micrometers is obtained by finding the line on the sleeve vernier scale which exactly coincides with one on the thimble. The number of this coinciding vernier line represents the additional digit. Thus, the reading for metric micrometers of this type is the number of whole millimeters and the number of hundredths of a millimeter, as with an ordinary micrometer, and the number of thousandths of a millimeter given by the coinciding vernier line on the sleeve vernier scale. For example, a measurement of 5.783 mm would be obtained by reading 5.5 mm on the sleeve, and then adding 0.28 mm as determined by the thimble. The vernier would then be used to read the 0.003 inch micrometers are read in a similar fashion. Note: 0.01 mm equals 0.000393 inch, and 0.002 mm equals 0.000078 inch, or alternatively, 0.0001 inch equals 0.00254 mm. Therefore, Metric micrometers provide smaller measuring increments than comparable inch unit micrometer. The smallest graduation of an ordinary inch reading micrometer is 0.001 inch. The vernier type has graduations down to 0.0001 inch. When using either a metric or inch micrometer, without a vernier, smaller readings than those graduated may of course be obtained by visual interpolation between graduations. Torque repeatability via torque-limiting ratchets or sleeves. A micrometer reading is not accurate if the thimble is over-decayed. A useful feature of many micrometers is the inclusion of a torque-limiting device on the thimble, either a spring-loaded ratchet or a friction sleeve. Without this device, workers may over-tighten the micrometer on the work, causing the mechanical advantage of the screw to squeeze the material or tighten the screw threads, giving an inaccurate measurement. However, with a thimble that will ratchet or friction slip at a certain torque, the micrometer will not continue to advance once sufficient resistance is encountered. This results in greater accuracy and repeatability of measurements, most especially for low-skilled or semi-skilled workers, who may not have developed the light, consistent touch of a skilled user. Calibration, testing and adjusting. Testing. A standard 1-inch micrometer has readout divisions of 0.001 inch and a rated accuracy of +/.0001 inch. Both the measuring instrument and the object being measured should be at room temperature for an accurate measurement. Dirt, abuse, and low operator skill are the main sources of error. The accuracy of micrometers is checked by using them to measure gauge blocks, rods, or similar standards whose lengths are precisely and accurately known. If the gauge block is known to be 0.7500 inches or plus or minus .00005, then the micrometer should measure it as 0.7500. If the micrometer measures 0.7503 inches, then it is out of calibration. Cleanliness and low torque are especially important when calibrating each tenth, or hundredth of a millimeter, counts. Each is important. A mere speck of dirt, or a mere bit too much squeeze, obscure the truth of whether the instrument is able to read correctly. The solution is simply conscientiousness, cleaning, patience, due care and attention, and repeated measurements. Calibration would not record the error at approximately 5 points along the range. Only one can be adjusted to 0. If the micrometer is in good condition, then they are all so near to 0 that the instrument seems to read essentially on all along its range. No noticeable error is seen at any locale. In contrast, on a worn-out micrometer, one can chase the error up and down the range, that is, move it up or down to any of various locales along the range, by adjusting the barrel, but one cannot eliminate it from all locales at once. Calibration can also include the condition of the tips, any ratchet, and linearity of the scale. Flatness and parallelism are typically measured with a gauge called an optical flat, a disc of glass or plastic ground with extreme accuracy to have flat, parallel faces, which allows light bands to be counted when the micrometer's anvil and spindle are against it, revealing their amount of geometric inaccuracy. Commercial machine shops, especially those that do certain categories of work, are required by various standards organizations to calibrate micrometers and other gauges on a schedule, to affix a label to each gauge that gives it an ID number and a calibration expiration date, to keep a record of all the gauges by ID number, and to specify in inspection reports which gauge was used for a particular measurement. Not all calibration is an affair for metrology labs. A micrometer can be calibrated on site anytime, at least in the most basic and important way, by measuring a high-grade gauge block and adjusting to match. Even gauges that are calibrated annually and within their expiration time frame should be checked this way every month or two, if they are used daily. They usually will check out okay as needing no adjustment. The accuracy of the gauge blocks themselves is traceable through a chain of comparisons back to a master standard such as the International Prototype Meter. This bar of metal, like the International Prototype Kilogram, is maintained under controlled conditions at the International Bureau of Weights and Measures headquarters in France, which is one of the principal measurement standards laboratories of the world. These master standards have extreme accuracy regional copies, and metrological equipment makes the chain of comparisons. Because the definition of the meter is now based on a light wavelength, the international prototype meter is not quite as indispensable as it once was. But such master gauges are still important for calibrating and certifying metrological equipment. Equipment described as NIST traceable means that its comparison against master gauges, and their comparison against others, can be traced back through a chain of documentation to equipment in the NIST labs. Maintaining this degree of traceability requires some expense, which is why NIST traceable equipment is more expensive than non-NIST traceable. But applications needing the highest degree of quality control mandate the cost adjustment. A micrometer that has been tested and found to be off might be restored to accuracy by recalibration. On most micrometers, a small pin spanner is used to turn the barrel relative to the frame, so that its zero line is repositioned relative to the screw and thimble. This calibration procedure will cancel a zero error, the problem that the micrometer reads non-zero when its jaws are closed. However, if the error originates from the parts of the micrometer being worn out of shape and size, then restoration of accuracy by this means is not possible. Rather, repair is required. See also, filler micrometer, vernier scale, references. Bibliography. External links, Open Source Physics Micrometer Computer Model, Simulator to Practice Reading and Interpreting 1/100th of a Millimeter Outside Micrometer, Simulator to Practice Reading and Interpreting 1/1000th of a Millimeter Outside Micrometer, print files including lessons and quizzes for teachers and students of the subject matter. Simulator to Practice Reading and Interpreting 1/1000th of an Inch Outside Micrometer, Simulator to Practice Reading and Interpreting 10,000th of an Inch Outside Micrometer, Quantum Laser Micrometers.